So, here's just an example. Here's a basis for R3. This basis is not orthogonal. You can take the dot product of any one of these with any of the others, okay? Dot product of this with either of the others is 1. It's not 0, not orthogonal, okay? Dot product of this with this one is 2, okay? So that's all your dot products. They're either 1 or 2. And you can verify that, think through it a little more slowly than I've given you a chance to, but you at least see that the dot products are not 0. They can't be. Okay, and dot product is commutative. So once I know the dot product of this with each of these, the dot product of this with this, I know the dot product of this with each of these, and the dot product of this with this, right? So I know all 6 possible dot products. Okay, so it's not, it's a basis, but it's not orthogonal. Okay? So we want to make it orthogonal. What we do is we project this vector onto this one, and then we subtract the projection. And we replace this vector with that. Now I'm going to draw it out geometrically. Okay, so like we've got. Here's V1 and V2. Here's the projection. Okay. I'm going to make a slight change. This one is a little too pat. Okay? So now V1 is a bit longer. And you can plot these easily enough. V1 and V2 are both in a XY plane. And the operations we do to do the projection and so forth don't depend on whether they're in the plane or not, but it's easy to draw it that way, okay? We know that angle's 45 degrees because of where these vectors are in the plane, right? Here's the projection. Now we did projections early. Remember doing them. It's projection onto V1 of V2. Okay? So if we do V2, well, here's the vector we want. This is a vector orthogonal to V1, okay? And V1 along with this vector spans the same space that V1 and V2 do, okay? Implicitly this is V1, V2, V3, but it doesn't really matter, okay? So, what is this vector? Well, the projection of V2 onto V1 plus the orthogonal vector equals what? This vector plus this vector equals what?
V2.
V2. Yeah, I know what you said now. You said 1, 1. Couldn't hear it. Okay? 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 Now this is parallel to V2, V1, right? So it's important to understand that. This is parallel to V1. This added to the projection gives you V2. And you can easily conclude that they span the same subspace, but you maybe have to prove that, okay? It should be pretty obvious that that's the case. Still needs to be proven. You never trust what you think is true. Test it by proving it, and we're working on that. Okay, so that's really important. Now, how do we calculate this orthogonal vector? Well, we can calculate the projection. That's easy enough. You might have to review how, but you knew it, you've done it. Okay? So you calculate the projection. And then how would you get the orthogonal vector? Well, you know the projection, and you know this vector, so how do you get this vector?
Subtract the projection from the vector.
Yeah. If this plus this equals this, then this equals this minus this. So, now there's a notation I want to use, but I don't know what notation your book uses, so I'm going to stop for a minute and take a peek at your book, okay? For the orthonormalized, actually, yeah, we do an orthogonal, then we normalize it, and that's very easy, but let me just look at the notation side, consistent.